Test. 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 Oh, fine. Alright, so, hey guys. My name is Runyan, and I'm going to give kind of synopsis overview of a talk I went to the other week. It was on the title was Special Relativity through animation. So, to start this off, you have to understand that linear algebra is the language of special relativity. So a lot of special relativity is based on vectors, methodology, calculus 2, Georgia Tech, eigenvalues, eigenvectors, those things. Also, another definition: frames. You have to understand frames. How two variables interact together, and that another important fact is that c, speed of light, is not relative. We can prove this in a laboratory through electricity and magnetism principles and experiments, I guess. An inertial frame is going to be identical at rest. Items in the frame are fixed. All pairs of frames are symmetrical at 0. Symmetrical speeds between the two frames. So for example, symmetrical speeds between two frames. If you have one object going this direction and one object going this direction, this is always positive and this is always negative. So this person is going negative in their frame, this person is going positive. And in this frame, this guy's going positive, this guy's going negative. So that's going to be constant. This is going to be negative symmetry. Okay, so the first thing the speaker talked about was the bug rivet paradox. So this is interesting because I couldn't find an image to describe it, so it's a little difficult. But basically, the principle explains that the paradox explains that motion of different frames can actually have different physical effects on objects. So if you have a rivet moving this direction and it hits a wall, the effect is going to be different if the rivet's stationary and the wall is moving towards it. So that's interesting. Next, the speaker spoke on slinkies, which is funny when you think about it at first, but it's actually very interesting. He spoke about how slinkies drop, and originally your thoughts might be that it drops at the same time, it compresses as it drops, or maybe the top meets the bottom, or the bottom meets the top. But what actually happens is the bottom, when you drop a slinky, the bottom stays stationary and the top comes down and meets it, and then they both fall together, which is really cool. There's a bunch of slow motion videos that the speaker showed, which were really interesting, and did a good job of explaining it. So if you're interested, look that up. It's well worth your time. Same thing happens. Same principle applies with like a golfer swinging their golf club. When they hit the ball, they don't feel anything, but after a minute or a second, fraction of a second, the force transmits up through the pole, and then they feel it. But they don't feel the force until after they hit the ball. Last topic the speaker touched on was the twin paradox. This is a kind of time paradox that relates high-speed travel to aging. So if you had two twins that were separated at birth, and one was put in a spaceship traveling at a substantial portion of the speed of light, and 50 Earth years later, the spaceship came back and the twins met. The twin that was traveling in the spaceship would only be 30 years old, while the twin that stayed on Earth would be 50. So that's an interesting phenomenon. And kind of to explain this, you have a graph. On the y-axis, you have time. X-axis is speed. So normally on Earth, your aging process is going to be vertical. It's just the time. But at higher speeds, your aging is more of it's a line, a linear transformation. So the way that works is you're going to age, the faster you're going, you're going to age less in an amount of time. So that's pretty much what the speaker talked on. One other thing he mentioned was how when you are moving at those different speeds, time is hard to judge. If you're in the spaceship, it looks like Earth is going slower. What happens is when you change speeds for a minute, time gets all messed up and things happen really fast on Earth. And then when you get back, you have that big time difference. That's pretty much it. Most of this is explained by the Minkowski diagram. That's the graph that I kind of tried to portray. So it was a great speech. If you're interested, look it up, Special Relativity through Animation. There's a book out there, and I hope you guys enjoy it.